This video illustrates a very basic statistical task, which is to compare results obtained in two experimental conditions. We use the same data as before, which is class scores in two different classes. So here we see the regular histograms in both conditions, the red and the black curve, or the corresponding cumulative distributions, which are matched here to the cumulative histograms found in these two conditions. Now let's start with the traditional way of analyzing such data, which is to perform what is called a t-test. There are actually two variations assuming equal or unequal variance. In the example case there's very little difference, so we just select the one using equal variance. So this is the traditional output. It says that the difference between the averages in the both conditions is 0.64. It also shows what is called an effect size, which is called Cohen's t, which is 0.46, which is actually can be converted in a just notable difference, and which often gets the annotation that it's a small size effect. So there's not a big difference between both conditions. The actual t-test shows that the t-value is 1.52, which is below the threshold value to reach significance, which should be 2.02, or equivalently, the probability of finding a difference of 0.64 if the two conditions would be the same is above 5%. It's actually 13.6%. Yet another equivalent way of expressing this non-significance means that the confidence interval for this difference runs from minus 0.2 to 1.49 and includes the zero value. There are all ways of saying that according to a traditional t-test, this difference is considered to be non-significant. Another piece of information is that for a small effect as the one here, you would actually need a lot more, and a lot meaning 4.7 times as many measurements to actually establish such a difference with sufficient power. This is a traditional output. Now let's see how we would do a similar test using the paradigm of log likelihood modeling used in ILLMO. So again, we go to the probability dialog box and we request the log likelihood profile for the difference between the two average values. So the log likelihood profile is shown here on the left, and intersecting this at the value of 3.84, we get the 95% confidence interval, which is reported here textually and which is rendered here graphically. It comes to the same conclusion as traditional t-test. The zero value is inside this interval, and so hence there's no significant difference. Again, we're not restricted in the ILLMO approach to only making the log likelihood profile for the difference. We can also construct it for the difference effect, which is the differences between the average divided by the standard deviations, which is similar to Cohen's t reported earlier. And we show that that log likelihood profile and the confidence interval derived from it, again, has zero included in it. Now ILLMO allows to either plot differences or difference effects. To change, we changed the plot option from relative between relative and absolute. So if we show the difference effect, we get the value reported here. If we switch back, we see the difference itself. Now, how can a difference effect like this be interpreted is that once we have modeled the two original histograms by Gaussian distributions, meaning showing we can use these distributions to create what is called a receiver operator curve, which is a very general way of expressing visually how well these two conditions can actually be distinguished. if we select that option, we get two parts of output. We get some textual output, which says, for instance, that Cohen's d is 0.47, as we've also found before, which says that the effect is small. So one of the interesting things, so the receiver operator curve is the black curve, and the area above that curve expresses actually the probability, which is called the probability of superiority. If we take a value from under the first condition and we take a value under the second condition, that's the probability, which is here of 63%, that the value in the first condition will be higher than the value in the second condition. So the probability is higher than 50%, but not a lot. That's why it's called a small size effect. Now, often, of course, in statistics, such as in a t-test, we don't base our results on a single measurement, but we base it on trial averages. And trial averages have much more pronounced differences in observations, which is reflected in that you can also make a receiver operator curve for the averages, and that the area to the right is actually a lot higher. It is actually 94%. So it means that if you base it on the averages, you have 94% chance that the average in the first condition will actually be higher than in